discussing the power developed in cylindrical generators. Cylindrical generator means the poles are non-salient ones and the rotor is a complete circular uh, cross section it is having, and there is no projected poles in the cylindrical generators. And normally this type of generators runs at a very high speed, and it is being employed in the turbo generators, that is in the mm, coal power plants and the nuclear power plants. So the topics to be covered are today the external characteristics of the alternators, power developed by cylindrical synchronous generators, the power output and the power input of the AC generators, condition for the maximum input and output power, and power equations neglecting the armature resistance. So the external characteristics of the synchronous generators are drawn between the armature current and the terminal voltage. So at no load, the voltage will be E only. Therefore, this is a flat line. And at unity power factor also, the terminal voltage drops a bit due to the internal drop in the generator, that is your reactance drop in the generator. Hence, you have even at the unity power factor, there is a slight drop in the terminal voltage for the given generator. But when there is a lagging power factor, the more the lagging power factor, the more drooping will be observed at the terminal voltage, while for the leading power factor, there will be certain increase, but later on it will come back to the level of the E, and as the more the leading power factor, the more time it will take to come to the actual level of the no load voltage. So normally the terminal voltage will be more when there is a leading power factor. So what do you observe is the external characteristics of synchronous generator shows the variation between terminal voltage and the variation of the load current. The no load EMF and the synchronous reactance is constant. Therefore, the terminal voltage is dependent on the armature current, and the magnitude of E is constant, but its phase angle is free to change. Okay, this is important. That is, the magnitude of E will be constant, but the its phase angle, that is the power angle delta with respect to the voltage, is free to change. So for unity power factor and lagging power factor, as the terminal voltage decreases as the armature current increases, and the terminal voltage also decreases as the power factor or the del angle also increases. While in case of the leading power factor, the terminal voltage increases with the increase in the armature current, and the terminal voltage decreases with the increase in the power factor and the delta angle. So now we will see the condition for the unity power factor, that is for the unity power factor load. This is the first case where we have considered some amount of armature current and the terminal voltage. This is your terminal voltage, this is the amount of the armature current, and due to the internal drop you get the induced EMF. This induced EMF will follow the circle which is given as the dotted line, and if the armature current increases, the terminal voltage will reduce. So over here you can see when the armature current has increased, the drop also increases and the del angle increases with the increase in the load, and the terminal voltage reduces. Now for the lagging power factor. Lagging power factor, the current is lagging the terminal voltage by an angle theta, and the internal drop will be given as IAxis, and this is your induced EMF which is having an angle del with the terminal voltage. Now the next we will consider that the armature current has increased. So with an increase in the armature current, the magnitude of the armature current has increased while the angle remains the same. The power factor is the same, only the magnitude of the armature current has increased. So with the increase in the magnitude of armature current, you see that this angle this reactance has increased and the terminal voltage has reduced. So the increase in the armature current will reduce the terminal voltage, and there will be an increase in the power angle del. The next will just change the power factor, keeping the armature current constant with respect to this figure. So when we increase the power factor, the del reduces, that is the power angle reduces, and this drop also is the same because the magnitude of this drop will be the same. This Ia axis will be the same, but overall terminal voltage reduces because the angle del reduces. Hence, the terminal voltage will reduce even the power factor increases. So, either the magnitude of the armature current increases or the power factor increases, the terminal voltage reduces in case of the lagging power factor. Now, this is the case of the leading power factor. So, when you have got a leading power factor, then this Ia will be leading the terminal voltage by an angle theta, and because the leading power factor, the terminal voltage will be more than the induced EMF in case of the leading power factor, because you have got the MMF in addition to the field MMF. Armature field will be additive to the field MMF. Now we'll see the effect of the magnitude of armature current. So if the magnitude of armature current increases, the del angle also increases and this drop increases. So the Vt will slightly increase, not much increase will be there because the angle will remain the as per the power factor, the angle remains the same. So there will be slight increase in the terminal voltage. Now the effect of the power factor with theta increased, now the power factor has been increased, the current is leading, the voltage is still, it is as compared to this, the magnitude is the same, but the power factor has been increased. So when you increase the power factor, the del angle reduces, but the magnitude Vt is still more, and therefore whether we either the magnitude increases or the power factor increases, the voltage will increase only, and but the del angle is different. The power angle is almost a little bit increases there in the power angle, that is the angle between the Vt and the E terminal voltage and the induced EMF of the generator, while the del angle reduces when there is an increase in the power factor angle. So now what is the power developed by the cylindrical rotors? Now we have got few terminologies, that is V is the terminal voltage, E is the excitation voltage, I is the armature or the load current per phase, phi is the phase angle considering the lagging one, and del is the load angle between V and E. These are the common nomenclatures we have been following throughout. So the synchronous impedance will be given for the inductive load as Zs is equal to Ra plus Jss, or Zs will be angle theta s, where theta s is the tan inverse of Xs by Ra. So this is the phasor diagram considering the armature drop and the internal reactance drop, which consists of both the leakage reactance and the armature reaction drop. Now taking the terminal voltage as the reference, that is we have taken voltage as the reference over here, V is at 0 degrees. So E will be at angle del, and your E will be V plus I Zs, that is the drop, impedance drop in the synchronous generator, and so the armature current will be given by E minus V by Zs, and this will be using for the calculation of the power. So now what is the power output of an AC generator? We'll first derive it in the complex form, and then we'll calculate the real and the reactive power separately. So that is given as P plus JQ, which will be V into I conjugate. Now why do you take I conjugate? Because if we just multiply V and I, the angle will be additive, so it won't be the angle between the voltage and the current. Hence when we take the I conjugate, the actual angle between the voltage and the current is taken into consideration, and that is what is related to the power factor of the given uh, power. So SOG will be equal to, substitute the value of the I. So it is E minus V by ZS conjugate, and then you substitute the polar values. That is, was represented as E angle del, V was represented as V angle 0, and ZS was ZS angle theta S. So when you divide throughout by ZS, you will get this, and because it is an conjugate, so in the next step we will take the we'll consider this conjugate, and this angle theta s is now positive. So theta s will be positive over here, and this theta s will be positive, and that is multiplying throughout by almost a negative sign to the angles, we get this expression. So the final expression of SOG comes to as VEZS angle theta s minus del, and V square minus ZS angle theta s. So this will be, from the polar form, will convert it to the rectangular form. So in the rectangular form, it is angle is given as represented as cos theta plus j sin theta. So that is what the representation has been done in the rectangular form. And when you segregate the real part and the imaginary part, this is the equation what we get it for the real and the imaginary part. And so the real part is the real output power, and the imaginary part will be the reactive power output. So for the real power output, we get the equation as, the real power output of the AC generator will be given as VE by ZS cos theta S minus del minus V square by ZS cos theta S. So where cos theta S is given by RA by ZS, and theta S is equal to 90 minus alpha S. So the what is the value of the theta s, substituting theta s equal to 90 minus alpha s, you will get this equation, that is, you will get POG is equal to V by ZS, and cos 90 minus, because theta s is equal to 90 minus alpha s, substitute that, rearrange the equation, you will get this equation, and this will be equivalent to cos 90 minus theta, so that will be 90 sine alpha s plus del. So this is the expression we are getting for the output power, or real output power of the AC generator. Now this is the per phase quantity. So for the 3-phase generator, we'll have the whole expression multiplied by 3, and that will be the total real output of the given AC generator. Now from the same previous equation, we'll take the reactive power, where we have segregated the real and the imaginary part. So again we'll follow the same steps, that is, now the theta s is equal to xs by zs, and theta s is equal to 90 minus alpha s. So you will get this reactive power as sine 90 minus this angle, so that will be converted to the cos, 90 minus x will be cos x. So you will get this reactive power generated in the AC generator in per phase quantities. So for the overall reactive power generated by the given machine will be multiplied by 3. Now come to the power input. So power input will be what? The power input will be now the induced EMF into the current conjugate. So the input power will be given as PIG. The notation, instead of O, we have changed it to E, that signifies the input of the AC generator, and then substitute the values in terms of the polar quantities and take the conjugate. So polar quantity conjugate means the minus of the given angle, so it is the angles are multiplied by the minus sign, and then we'll convert this to the rectangular form, where we'll get the real and the imaginary quantities, and the angle will be written in the terms of the rectangular quantities as cos theta plus j sin theta. So the same has been applied, and now we will segregate the real part and the imaginary part and try to equate with the real input power and the reactive input power. So the real input power to the AC generator will be again the same thing. We'll have cos theta is equal to R by Z, and theta s is equal to 90 minus alpha s. Substitute it and you will get the input power as E square by Z square Ra minus VE by Zs sine del minus alpha s. Now this is per phase quantity. So for the 3 phase, multiply the whole equation by 3. Now the reactive input power of the AC generator, the imaginary part we have taken from the total power, and therefore again we will substitute the theta s is equal to 90 minus alpha s, and the input power you will get it as Qij is equal to E square xs by Zs square minus VEZs cos del minus alpha s. And for the 3 phase generator, again multiplied the whole equation by 3. So the mechanical power input to the AC generator is, power input in the mechanical terms will be equal to power input to the generator plus the friction and the windage losses plus the core losses. So the mechanical losses and the core losses has to be taken into consideration to calculate what should be the mechanical input power to the generator to produce this output powers. So now we'll try to find out the condition for the maximum power output. So because del is the variable quantity depending on the load, so we'll differentiate this equation by with respect to del, and the first differentiation should be equal to 0 and the second differentiation should be less than 0 to find out the maximum power output. Now when you differentiate the actual equation with respect to del, over here we will be having some few constant quantities, that is your E, that is the induced EMF, the voltage, the impedance and the resistance will be all as the constant quantities. The only variable is the angle del. So when you differentiate this equation with respect to del, you will get this VE by Zs cos alpha s plus del is equal to 0. So this can't be equal to 0. So the cosine term will be equal to 0. This means that alpha s plus del should be equal to 90. That is when del is equal to 90 minus alpha s, that is the impedance angle, then your output power will be maximum. So the load angle, when it is equal to the impedance angle, you get the maximum power output. Now substitute this value in the final equation. So when you get what you get as the maximum power output of the generator is the VE by Zs minus V square by Zs square into Ra. So now the condition for maximum power input, again the variable quantity is the del, so we'll differentiate the equation with respect to del. The second differentiation has to be less than 0. So after differentiating it, the equation, the real power equation, you will get some constant terms. So because of the constant terms, the differentiation will be as VE by Zs cos del minus alpha s. Again the VE by Zs can't be 0, so the cosine term will be equal to 0, which gives the result as del is equal to 90 plus alpha s. So that 90 plus alpha s means we can write it as alpha s is equal to 90 minus theta s, so del will be equal to 180 minus theta s. So the input power will be maximum when the load angle is 180 degrees minus the impedance angle. So the maximum input power can be obtained by substituting the value of the del, and we get it as E square by Zs square Ra minus V by Zs is the maximum input power that is possible for the generator. So now when we neglect the armature resistance in the equations what we have derived, so our R will be 0 and therefore the impedance will be equal to the reactance and the alpha s will be also equal to 0. So the real output power becomes VE by Xs sin del. The reactive power output becomes VE by Xs cos del minus V square by Xs, and the real input power is your VE by Xs sin del, that is the same as the real power output, and the reactive power is E square by Xs minus VE Xs cos del. Okay, so these are the different terms which we can or a shorter form when we neglect the armature resistance for the given consideration, and therefore we can conclude that when we neglect the armature resistance, the output power maximum and the input power maximum is equal to VE by Xs sin del. That is, the input will be also maximum and the output will be also maximum by and it can be given by the equation V into E by excess sine of the power angle. So this is the expressions what we have calculated for the different powers. So we have calculated the power for the cylindrical synchronous generator, the input and the output power of the AC generators, condition for maximum output, input and output power, and the power equations, neglecting the armature resistance to make the equations simpler. So thank you.